Hi folks, and welcome to our first pre-recorded lecture. This will be Chapter 4, Forces Between Particles. Up until this point, we've pretty much just been talking about what happens within an individual atom. We've learned about isotopes, we've learned about electronic configurations, we've talked briefly about the concept of valence shell electrons, but now we're going to start talking about what happens when one atom interacts with another atom. There's two main ways this can happen, and when those atoms interact, we start getting things called molecules or compounds. So we have ionic, in which case one atom will give up electrons and the other will take it. So in this case, our little cartoon here has one atom proposing to another. Or we can have covalent, or sometimes also called molecular compounds. And this is where atoms share their electrons. So as always, please make sure you're doing your reading. We're going to cover some topics in depth here, but there are things that we are going to kind of let you kind of munch on your own. Next time we have class, I will open class up with questions. That would be a really good time to bring up anything that you have questions about regarding reading or anything like that. You can also come to office hours or just email me, or you can ask it to the general discussion board on Canvas as well. So the first topic we're going to talk about are Lewis dot structures, and these are pretty straightforward and simple. It simply is a way for us to represent different valence shell electrons. And think about when we do electronic configuration. We know that the valence shell electrons, for the most part, right, when we're dealing with this, unless we're dealing with crazy transition metals, the valence shell electrons compose how many electrons are in the S and how many are in the P. So, for example, we have here magnesium. When we do a Lewis dot structure, we just use whatever the symbol is for the element that we're talking about. So in this case, Mg. And we know that magnesium has two valence shell electrons because it only has two electrons in its S and none in the P. And so we can write it a couple different ways. All of these are correct in how they're written. Typically, I would say most people will fill their Lewis dot diagram kind of in a clockwise or counterclockwise fashion. This is correct, so is this. It's just convention often has people do something like this. So if we look down here, for example, carbon. Carbon has 4 valence shell electrons, right? Think about it. Think about the electronic configuration of carbon. 2s2, 2p2. So that's 2 in the s orbital and 2 in the p orbital for a total of 4 valence shell electrons. Now, what we see here is when we do a Lewis dot structure, it's kind of like 4 quadrants. Once we move on to nitrogen, which now has 5 valence shell electrons, because now there's 3 electrons in the p orbital, we start having to double up, just like we do when we do the arrow diagram filling for our electronic configurations. Sorry, I just kind of blanked out there for a second. Right? We don't double up until we have to. Same thing happens here, all the way to our noble gases, where we start seeing our 8 valence shell electrons. Now, obviously, helium and hydrogen, they're so tiny that helium is a noble gas and it's fully satisfied with just 2 valence shell electrons, and that's fine and good for helium. So when we think about kind of differentiating elements and compounds, right? We talked about in the previous lecture the concept of the difference between a pure substance and a mixed substance or a mixture. With impure substances, we can have 2 kinds or 2 flavors of pure substances. We can have elements and compounds. Now, most people are comfortable with the concept of a pure substance being an element. It's like not rocket science. It's like, okay, whatever I'm holding or looking at, the sample I have, the only atoms present in there are one type of element. That would make it pure. 95% of the time, people are thinking of an atomic element. So an atomic element is, for example, we have a sample of neon gas here. If I had my magic tweezers and could pull out one atom, I could look at that one atom of neon gas and be like, yep, that's neon. this atom of neon is the same as all the other atoms of neon. Great. Now, in nature, something kind of kooky happens. There are 7 elements that don't like to exist by themselves. What I mean to say is, this sample of neon gas, right? There are a whole bunch of individual atoms of neon hanging out in that sample. It's not by itself in the fact that, there's billions and trillions of other neon gases hanging out, neon atoms hanging out in this gas sample. 7 elements, however, can't handle just hanging out by themselves, even if they have other ones around them. For example, oxygen. Oxygen is what we would call a molecular element. The molecular element in nature doesn't usually exist as a single atom. They exist as what we call a diatomic molecule. Di standing for two-atomed molecule, right? So in nature, you won't just find oxygen hanging out by itself as a single atom. You will find it as O2. This is really important to remember when we're doing our chemical equations, or like anytime we're doing dimensional analysis, right? Where we're going to have equalities and ratios, where if I'm told in words, maybe I have a word problem, and that word problem says I have, 5 moles of oxygen gas. Well, when I'm writing out that equation and trying to balance it and figure out what's going on, if I forget that oxygen is diatomic, my ratio is going to be off because it's actually O2, not O. So that's something important to keep in mind. The other kind of pure substance that we're going to look into more detail, and this kind of, these things over here are kind of what we're going to talk about today, are molecular, also known as covalent compounds, and ionic compounds. And we're going to talk about the differences between the two of these. So again, to give you kind of a concept of that difference between an atomic element and a molecular element, we're just talking about the idea that atomic elements are okay hanging out by themselves, and that diatomic elements need to be kind of in a base unit of 2. And so here are the 7 diatomic elements. You should be comfortable knowing what those are. And be aware that on tests, quizzes, homeworks, all that kind of stuff, there won't be too much kind of hinting that something is diatomic. It is expected that you will know that. First typo of the evening, ionic and covalent compounds. This should say compounds. So we're going to talk about 2 different flavors of compounds. Ionic and covalent. Like I said, sometimes covalent is also written as molecular. They're interchangeable words, so depending on what resources you're using, your book versus some YouTube videos or whatever, it might go back and forth, but they're the same thing. So each of these kind of have their own recipe. We're first going to start with ionic compounds. Ionic compounds are formed, the recipe for an ionic compound will always be some metal or metals giving up electrons to some nonmetal or nonmetals. And when we say nonmetals, this could also be polyatomic ions. This would count as a nonmetal. And so let's use the example we have here of table salt, NaCl. Table salt is an ionic compound, and we know that how many valence shell electrons would sodium have? Go ahead, go look on your periodic table. Go, right now. It should be out in front of you. How many valence shell electrons does sodium have? It has 1. 1 valence shell electron because it has only 1 electron in its outermost s orbital. Look on your periodic table. How many valence shell electrons does chlorine have? Count them. 2 in the S. How many in the P? 5 for a total of 7. So we have 1 valence shell electron on our metal and 7 valence shell electrons on our nonmetal. It's a lot easier for sodium to give up that 1 valence shell electron, and it's a lot easier for chlorine to accept a valence shell electron. Each of these filling their, satisfying that full outer layer, right, than for chlorine to give up 7 electrons and sodium to gain 7 electrons. So when we lose an electron, we're losing a negative charge, which means our atom now has more protons than electrons, which would give it a positive charge. When the chlorine accepts an electron, it's now going to have more electrons than it has protons, which will give it a negative charge. And what do positive and negative charges do when they're near each other? They're attracted to each other, right? They're electrostatically attracted to each other, just like magnets. So we have a plus charge and a minus charge. Shabam, they come together. And they are electrostatically attracted to each other, and that is what the ionic bond is. Ionic bonds are very, very strong. Here we see examples with polyatomic ions. Same concept is still occurring here. The other kind of compounds that we're going to talk about a little later are called covalent compounds, right? Now, the recipe for a covalent compound is nonmetal bound to another nonmetal. So we're only going to be looking at a very tiny corner of the periodic table in terms of the elements that we're going to be playing with. However, there is an incredibly diverse and vast number of covalent compounds. One of the classic examples we will use over and over and over and over again is water, H2O. These nonmetals will share their valence shell electrons so that everybody kind of gets to feel like they have a full octet, that full 8 valence shell electrons. So in both cases of covalent and ionic compounds, right, the atoms are trying to get more stable. They're trying to form octets, right, by either losing, gaining, or sharing their valence shell electrons. So for example, in an ionic bond, the M is just standing for metal, the NM is standing for nonmetal. The metal will give up the electron and become a positive charge. The nonmetal will accept the electron, becoming a negative charge. Positive is attracted to negative. This is an ionic bond. When two nonmetals share an electron, or a pair of electrons, I guess is the more better way to explain it, what we have going on is each of these atoms gets to say they quote-unquote own both of these electrons. So this nonmetal gets to say, yep, I've got an octet, 2, 4, 6, 8 valence shell electrons, and this guy gets to say 2, 4, 6, 8 valence shell electrons. So that overlap occurs, and this overlap where they're sharing those electrons is what we would call a covalent bond. So again, here we have an example using our noble gases, helium, neon, argon, krypton, right? When we go through, we know helium is super tiny, so it's actually happy with those 2 valence shell electrons. It's the only one that does that. But after that, 8, 8, 8, everybody's trying to get to 8. Remember, we're always looking at the S and the P, S and the P. Those are what tell us what the valence shell electrons are. Don't worry about the D. Remember, that's 3D. The outermost shell is still the 4. So, how do we kind of call out these positive charges, these negative charges when we're dealing with ionic compounds? So when we have a positively charged atom, something that has lost electrons, we now call it an ion. It's no longer an atom. An atom is a neutral neutral particle. An ion is a charged particle. Now, we go even further and determine and have special names for the positive ion and the negative ion. The positive ion are called cations. Now, this is very silly, but you will never forget it. Cations are positive, like the little cute paws on a cat. Okay, if you want to do like a little meow every time you see a cation, I know it sounds very silly, but you will never forget it and you will never confuse them. Cations are positive, okay? That is the positive charge, which means it is losing electrons. It might lose 1 electron, in which case it would have a +1 charge. It might lose 2 electrons, which would give it a +2 charge, or it could lose 3 electrons. Now, when we get into the transition metals, they can actually lose a lot more than 3 electrons, and we'll talk about that. I'm not going to go into too much detail with it, and you'll be able to do more of that in your reading, but we'll look at it. So let's look at what's happening when a cation is formed. So here is our sodium atom, right? Atom, it's neutral. We know from our previous class that a neutral atom is going to have the equal number of protons as it does to electrons. When it loses one of those electrons, we now have more protons than we do electrons. This means that we now have an abundance of protons, so more positive charge than negative charge. When we have that, we're going to have an overall positive charge to the atom, giving us a cationic charge of 1 plus. What happens when we lose 2 electrons? For example, magnesium. We look at magnesium, find it on the periodic table. We see that it's going to have 2 valence shell electrons. There's the Lewis dot structure. There's the electronic configuration, right? We have 2 electrons in the 3s. And so it's going to be easier for this atom to get rid of these 2 electrons and have a full octet here than it's going to be for it to gain 6 more. So when it loses 2 electrons, we're now going to still have that 12 protons, but now we only have 10 electrons, which means we have an overall positive 2 charge. Now, one thing I want to show you here, you've noticed in both of these cases that we had this bigger circle and it becomes a smaller circle, bigger circle to a smaller circle. Think about our periodic trends. When we lose electrons, right? We're losing an outer shell here, right? Like a layer in our onion. So this is going to be a smaller radius now of our ion. So cations are smaller, right, than their parent neutral atom. The nonmetals will form a negative ion when they gain an electron. So they go from a neutral atom and gain electrons, and we call those negative ions anions. So we have cations and anions. The nonmetal or the polyatomic ion will always be the thing that will take on the electron. The the metal, the cation, will be the thing that gives up the electrons. So the same thing is happening in the formation of an anion. It's gaining extra electrons, so it's becoming more negative. So here we have chlorine becoming the chloride anion. 17 and 17, right? It gains a valence shell electron, and now we have 17 protons still, but 18 electrons, which means we're going to have an overall -1 charge. So here is just kind of a little chart to kind of help go through this. It kind of goes hand in hand with what we've been learning previously in dealing with electronic configurations. Right? Everything in the 1A group, our alkali metals are going to form +1 cations. Alkaline earth metals will form +2. 3A, the only one we're really going to deal with is aluminum, +3 charge. And then on the non-metal side, when we go nitrogen, oxygen, fluorine, we're going -3, -2, -1. So ionic compounds, like we said earlier, ionic bonds are very, very strong. They're very, very strong bonds. I want you to think in your experience, have you ever seen table salt burn? I mean, like catch on fire burn. Probably not, right? It's not something that can easily happen. It's not going to catch on fire. It's not going to melt. It's not going to boil. It's certainly a solid at room temperature. Now, that's melting is different than dissolving in water, and we'll talk about that later. But I'm talking about if I heated up table salt. It's not going to melt like butter does or something like that. And if I, put a blowtorch on it, it's not going to catch on fire. That's because ionic compounds have these super strong bonds from that positive and negative attraction to each other. So when we have an ionic compound, the formula for that ionic compound is dictated by the charges. So in a neutral ionic compound, something where there's no additional charge, we're going to have the positive charges always equal the negative charges. In something like sodium chloride, NaCl, that's pretty easy. The Na is going to give up one electron and become -1, and the chlorine is going to gain that electron and become, the sodium will lose an electron and become +1, the chlorine will gain the electron and become -1. So the positives equal the negatives. That's a pretty straightforward one, but what happens when we have something that's a little more complex? For example, what if I had magnesium chloride? Now magnesium is going to form a +2 cation. It needs to get rid of 2 electrons. But chlorine on its own, a single atom of chlorine, would only want to take on 1 electron. So we would need 2 chlorines to accommodate 1 magnesium. The magnesium gives 1 electron to one chlorine, and the magnesium gives the other electron to another chlorine. So we end up with a +2 on the magnesium, and each individual chlorine gets a -1. Overall, we still have -2 + 2. It equals out. So when we're writing ionic formulas, we want to use this concept of charge balance, right? This positive charge equals negative charge. That's going to always guide us when we're doing our ionic compounds. And it's one of the things students struggle with a little bit when it comes to formulas. Ionic compounds, you have to understand the charges to be able to take something like sodium nitride and be able to know what the formula for that is. You have to go, oh, sodium. All right, that's Na. That's going to be a +1 charge. Nitride is going to be nitrogen. Well, nitrogen makes a -3 charge. Well, I'm going to need 3 sodiums for every 1 nitrogen, which is how I would get something like this, Na3N. Now, remember, the 3 here belongs to the Na. When it's a big 3 or a big number in front, that means that it accounts for all of it. The little number always goes to the element right before it. So when we look at something like sodium sulfide, again, we know sulfur is going to be a -2, a -2, and sodium is going to be a +1. So we're going to need 2 sodiums for every 1 sulfur. So when you're going through and trying to figure out the charge, or the formula for an ionic compound, there's some simple rules we can follow. The first thing that you need to do is be able to identify what elements or polyatomic ions are going to be present in the compound. For example, let's say I have something that is going to be barium chloride. Okay, I'm going to have barium and I'm going to have chlorine. First, I should write down the symbols of each ion. Barium, Ba, chlorine, Cl. Go and figure out what are the charges on each ion for that. Looking at the periodic table is a really good way to do this. Barium is going to be a +2, chloride is going to be a -1. Now I need to balance it. If I have a +2 here, I'm going to need -2 overall on this side, which means I would need 2 chlorines. Therefore, I can write it like this, BaCl2. The 2 represents that I have 2 chlorines. Now, this is kind of a nice cheat sheet. Basically, it follows the patterns that we've been talking about. The tin and lead down here, we'll talk about a little bit more when we talk about the transition metals. But basically, the 2 that you want to consider are going to be the metals and the nonmetals, right? That this is the recipe for an ionic compound. Metals giving up electrons, nonmetals accepting them. You will be expected and must be able to write a formula for an ionic compound from the name and to take the name of an ionic compound and write the formula. Most students find one way to be easier than the other, but you really should practice both. Your homework is going to be a really good source of practice for this. Because it's naming, spelling will count. And especially because we're in an online situation right now and you can have open notes on your assessments, there will be no partial credit for misspelling things. The names are the names, and as I said, because we are going to be in an open note situation, spelling will count. If you need to discuss that with me further, please let me know. So, an ionic compound, right, we're always going to write the metal first. So it's always going to go cation, then anion. So metal, then non-metal. And when we're writing the metal, we just say the name of the metal. So for example, in Ki, it's going to be potassium. The non-metal, we're going to chop off the last syllable of the element and add "ide" to the end of it. So in this case, Ki is potassium and iodine, but we have the ionic form of it, the anion, so it's going to be chopping off the end of it and calling it potassium iodide. +1, -1. Charge balance. For something like aluminum oxide, this is a little harder. We have a +3 charge and a -2 charge. Ay, right? That's not like super easy right off the bat to kind of think about what is it going to be for a formula where the plus charges equal out the minus charges. There's a couple different ways people do this. There are some simple little cheats people use, but basically you want to think about lowest common multiple. 3 and 2, what's the lowest common multiple between 3 and 2? 6. So we need everything to equal 6, which means I would need 2 aluminums to get a +6, and I would need 3 oxygens to get a -6. Again, these are kind of the rules by which you can use to identify how you're going to name a compound. So I'm going to leave these up for you guys to go through. It's essentially what we just did, but I have it written out for you with a lot of really nice examples to kind of help you through them. I want to talk now about the transition metals. So transition metals, just like in our electronic configurations, kind of give us some funkiness and some challenges. Those challenges proceed into what we can expect when we're doing the naming. Now, as I've said before when we were doing the electronic configurations, your homework will be more challenging than the tests when it comes to dealing with transition metals. It's just to kind of get you to push yourself when you have unlimited time and tries, and then on tests and quizzes, we won't be as exact in what we're asking for. So transition metals have the ability to give up different amounts of electrons, unlike something like sodium, where it's always going to be a +1 cation. Something like iron has a couple different configurations it can make. And those different configurations we're not going to go into too much detail with, but basically it has to do with energetics. It's depending on the situation and that weird d orbital kind of axis that it can reconfigure itself to easily give up 1, 2, or 3 of its valence shell electrons. Something like gold can give up 1 or 3. Which is weird. Zinc will always be +2. Zinc will always be +2. Copper can do +1 or +2. Nickel can do +2 or +3. Tin can do +2 or +4. Now, I would strongly suggest you add this to your notes. It's not something you have to memorize. We're going to show you some tricks and hints and tips on how you figure out the ionic formula for transition metal containing compounds. So the first thing we need to deal with when we have a transition metal in our ionic compound is how we're going to write it. So we just discussed that when you have a regular binary ionic compound, that you name the metal first and you just use the full name of the metal. So the example we did of potassium iodide, Ki. Well, when it's a transition metal, we're going to have to add an extra feature to it. We're going to have some Roman numerals. The Roman numerals are going to represent the charge associated with that metal, and that's because it could have different charges. For example, we talked about the fact that iron could be +2 or iron could be +3. When we're dealing with the +2 form of the iron, it will be written like this, iron 2 is how we say it, but it's iron with the Roman numeral 2. If we have the iron, the +3 form of the iron, it's written like this, iron 3. So, for example, iron 2 chloride. Iron 2 chloride, the Roman numeral here tells me that I have Fe2+, right? If I have 2+ and I'm using chlorine, each of those chlorine atoms will become an individual chloride, right? So we need 2 of them to account for the 2 irons here. Iron 3 oxide would be Fe2O3. If I had iron 3 chloride, it would be FeCl, what would it be here? If it's iron 3 chloride, FeCl3. So again, we can use these rules to kind of help us name something that has a transition metal in it. Please excuse me, my allergies are really out of control tonight, so I hope I'm not sounding too nasally. So again, this will be something where students find often that they are better going either from the formula to the name or the name to the formula. Typically, you struggle one way or the other, and everybody's a little different, but give it a shot. The last type of formulas for ionic compounds that we're going to talk about are those with the polyatomic ions. So I would again strongly encourage you to print out and have this as part of your notes, the polyatomic ions. Remember, on tests and quizzes you won't be able to have your slides available for you. It's hard written notes, so print this out and use it to write some notes on. But they're ions, so we're going to treat them in the same way that we did when we had a non-metal or a metal. Now, the only polyatomic ion that forms a cation is ammonium. Everything else is an anion, which means ammonium is the only one where we would have it come first in the name. Everything else would be, the secondary part of the name. But again, you don't need to necessarily memorize these. The more you do them, the more you will, kind of just know them. But when we have a polyatomic ion, we're going to keep the whole polyatomic ion together. So for example, I've color-coded this. If you are someone who has trouble with distinguishing colors, please let me know, and I will provide you with a different set of slides for this section. But for example, let's say we're looking at potassium nitrate, KNO3. In this case, we know the cation is the potassium, and the polyatomic anion here is nitrate. KNO3, potassium nitrate. Potassium is a +1 charge, nitrate is a -1 charge. FeOH2. If I just gave you FeOH2 and I wanted you to name it, the first thing your head should be thinking is, oh man, iron. This is iron. That's a transition metal, so I'm going to have Roman numerals in there. So I've got to kind of use that different set to go through. And we'd say, okay, well, OH is a polyatomic ion, and I know that hydroxide OH is a -1 charge. So if it's a -1 charge and I have 2 of them, that means my overall minus charge is going to be -2. and I only have one iron, which means this must be +2. So we're going to have iron 2 hydroxide. The last example I want to give is one where it's a little crazy, right? We have a cationic polyatomic ion, and we have a lot of anionic ones. So it's actually possible to write an ionic compound that is made up of entirely polyatomic ions. Ammonium nitrate is an example of this. Ammonium is going to be the cation, and nitrite would be the anion. This is kind of just a nice flow chart to help you with dealing with these ionic compounds and how to name them. So I'll just kind of leave that up here. From here, we're going to move on to covalent compounds. So if I know I'm kind of talking quickly through this, but since it is a pre-recorded lecture, if this is a point at which you need to stop, kind of collect yourself, go back, look at some notes, try some practice examples, I would encourage you to do that. Hit pause and come back when you're feeling confident to move on to covalent compounds. All right, so covalent compounds. We know that covalent compounds, the recipe for covalent compounds is going to be 2 or more nonmetals bound together. And the way they bond is through sharing their electrons to complete their octets. This is also how our diatomic molecules are made. Remember at the beginning of this lecture we talked about the diatomic molecules, the 7 diatomic molecules. If you start looking at their Lewis dot diagrams, you'll notice that all of them kind of make sense why they are diatomic. Hydrogen, for example, is diatomic. Each hydrogen has only one valence shell electron. We know hydrogen's so small that its full, complete outer shell only has 2 in it. So if we have 2 hydrogens existing together, it's so much more stable and happy to just kind of hang out together. But it's also a good example of a diatomic or covalent molecule. Here's another example of a diatomic, fluorine, right? Here are the Lewis dot diagrams for 2 fluorine atoms. We know fluorine, and you look at the periodic table, has 7 valence shell electrons. It only needs 1 more to complete its octet. It makes a lot of sense for 2 fluorine atoms to share a pair of electrons, giving them a covalent bond so that each of them can say they have a full octet. Now, when they share a pair of electrons, we often write it with just a line like this, but you can pretend there are 2 electrons hanging out in that bond. From here we can get into a lot of pretty crazy molecules, and this comes in the form of covalent bonding between different types of atoms. Here we have methane, CH4. This is basically your farts. And we know that each hydrogen atom wants 1 electron. 1 more electron to be happy, right? It has 1, it needs 1 more. Carbon, on the other hand, has 4 valence shell electrons. It needs 4 more, so it's going to make an individual covalent bond with 4 different hydrogens to achieve that. So here are the guidelines that we have when we're helping to figure out how to draw these covalent bonds and draw these covalent compounds going away. This is the foundation of Unit 2. So this is not something that you want to gloss over. First, you're going to need to look at the atoms that you have and arrange them in a way that you think is going to make sense. And then you would determine the total number of valence shell electrons between all the atoms. We're going to attach a bonded atom to each central pair with a pair of electrons. So basically, we need a way to connect all the atoms. Then the remaining electrons are kind of dispersed so that we complete as many octets as possible. If we can't make an octet, then we start forming multiple bonds or sharing multiple pairs of electrons till we can get there. So we can have a multiple bonded system. We can have a single bond where 1 pair of electrons is shared, a double bond where 2 pairs are shared, or triple bond where, you guessed it, 3 pairs of electrons are shared. I have a really good resource worksheet for you guys in the resources section for Unit 1 that goes into a lot of detail with a lot of examples on drawing covalent compounds, so I encourage you to look at it. We'll go through and do a dot diagram for this carbon disulfide just to kind of help give you some grounding in what we're talking about. So step one is to determine the arrangement. Oftentimes there's some rules you can kind of think about when you're trying to figure out what's going to be your central atom. Carbon makes a really good central atom. It's often a central atom. So if you have a carbon in your formula, that's a good place to start. Terminal atoms would be the things on the ends of our compound. Halogens, chlorine, fluorine, bromine, iodine, those are all going to be really good terminal atoms because they all have 7 valence shell electrons, so they're only going to make one bond. So if they can only make one bond, they're going to be pretty terrible central atoms if there's more going on. So that kind of helps guide things, and there's going to be trial and error with this, and that's okay. The more you do these, the more patterns you'll see, and you'll kind of just start getting like a sixth sense about like how they should be kind of built. So once we have what we think is a solid arrangement of what it should kind of look like, we need to go through and determine the total number of valence shell electrons for the whole thing. In this case, we know we have one carbon, which has 4 valence shell electrons, and we have 2 sulfurs. Each sulfur is going to have 6 valence shell electrons, and we have 2 of them, so that's a total of 12. 4 plus 12 gives us 16. So now we have to start using up those 16 valence shell electrons. The first thing we want to do is connect everything. So we want to share a pair and make a bond between the sulfur and this carbon and the carbon and this sulfur. In doing so, we eat up 4 of our 16 electrons. So we have 12 electrons remaining. So now we're going to go through and fill up everyone else's octets on the outside first. When I do that, I need to use 12. 2, 4, 6, 8, right? Oops, it looks like it didn't show up here. 2, 4, 6, 8, 10, 12. So we need still a couple more places where we can complete our octet. And to do that, what we're going to do is have to use multiple bonds. So what we're going to do is take an extra set of our lone pairs down here to complete our double bond. So it's going to be S double bonded to a carbon, double bonded to another sulfur. And again, I have a lot of very detailed resources for you on our Canvas page, writing out these covalent compounds. So naming covalent compounds, there's a little more to memorize, but it's a lot simpler than our ionic compounds. So basically, because we have 2 nonmetals, we aren't looking at the charges or anything like that. So we're just basing it off of the name. And so we're going to have to tell how many of each we're going to have. So the first nonmetal we name by its element. So for example, if we have NO, it's nitrogen oxide. The second nonmetal is going to end in "ide." We add these prefixes to say how many of them we have. So for example, if we have NO2, nitrogen dioxide, or dinitrogen oxide, or dinitrogen tetraoxide. So you should be comfortable between 1 and 10 in knowing those. So here are 5 different compounds that have very different properties, very different uses, physical properties to them, chemical properties to them, but they all contain just nitrogen and oxygen, just in different ratios. One of the last things we're going to talk about in this chapter are naming acids. So we're going to have a whole chapter dedicated simply to the behaviors of acids and bases, but we're going to talk about naming them right now because they fall under covalent compounds, and it'll be good for us to know how to name them now. That way when we actually start talking about how to use them, that we know which ones we're talking about. So whenever we're naming an acid, the first thing we need to do is identify it as an acid. And acids are going to be molecular compounds that form ions when they dissolve in water. And again, we'll kind of talk about this in more detail as we get going. But some of the tricks and hints that you can look at when you have a compound and you see AQ as the state of matter that it's in, that's a pretty good sign that we're dealing with an acid. So HCl, you might be familiar as being an acid. HCl-AQ would be the acid. HCl, the gas, is a different compound entirely. And that can be tricky to be comfortable with. And this is why I'm always stressing that when you're writing in a formula, you need to write the states of matter. They're really important. So when we have these binary acids, they're going to be composed of hydrogen, and that's usually going to be written first in the name, and then it's going to have one or more nonmetals, or sometimes it will have a polyatomic ion with it, and we'll talk about those more. So we're going to have the hydrogen, which we're going to call hydro, and then the base of the nonmetal with ic, and then we end it with acid. So for example, we have hydrochloric acid or hydrobromic acid. If we have H2S, this would be hydrosulfuric acid. And you might be struggling with this because you're looking at it going, oh, H2S is an ionic compound. Yes, we're dancing around the ionic compound, but it's not. It's going to have different properties than a traditional ionic compound. NaCl table salt is not going to react the same way H2S, the aqueous solution, will. But for right now, we're just kind of talking about the nomenclature. Like I said, we will have a whole chapter dedicated to acids and bases a little later. Oxyacids are a different kind of acid, and these use the polyatomic ions that contain oxygens. That's why they're called oxyacids. And this is kind of a little like memorization device called aticitis. It's the acid disease, aticitis, right? Like you can kind of use that to help you memorize this. So when we have the 8 version of a polyatomic ion, for example, nitrate, sulfate, chlorate, it will end in ic. Chloric, sulfic, nitric. If we have the ite form of the polyatomic ion, nitrite, sulfite, chlorite, it will end in us. Ate, ic, ite, us. That is the little quick way to help you memorize how you would name these oxyacids. So again, this is a really nice kind of flow chart to help you when you're kind of going through nomenclature. It'll be helpful for your homework. Again, really what it comes down to is you are going to have your homework be really vital in practicing these. The more you practice this, the better you will become at it. I know right now this is really challenging, and especially at the speed we're going at for this class, it's very hard. But in a couple weeks, we will have been using this nearly on a day-to-day basis that you will be more comfortable with it. The more practice you do, the more comfortable you will become with it. Just like any language. This is a language. This nomenclature is a language. These formulas is a type of language. The more you use it, the more you will become familiar with it, where all of a sudden, even when you've never seen a formula before, you'll kind of look at it and you'll be able to tell something doesn't seem right about it, or it just doesn't sound right saying it, mixing it up. And so it will become second nature if you go through and do your practice. The last topic that we're going to talk about for chapter 4, we're going to be dealing with some periodic trends. So we know that the periodic table is a very, very powerful tool for us in terms of telling us so much information without having to, write it all out. We can utilize the table. So we're going to start talking about some trends that we also see within the periodic table. The first trend we're going to talk about is electronegativity, and this is the attraction of atoms for shared electrons. So electronegativity will increase as we go from left to right, and this should make sense, right? Think about it. Does a lithium or a beryllium, do those want electrons? No. This has one valence shell electron, and this has two. It is way easier for them to give up a couple of electrons than add them. So their electronegativity, their desire for shared electrons is very, very low. They don't want them. Something like fluorine really, really wants electrons, right? Whether it's given to them completely ionically or sharing them, it's one electron away from being able to have a complete octet. So it really, really wants it. This trend from left to right is pretty easy for people to kind of understand. The other way that we need to talk about the trend is as we go from bottom to top, electronegativity increases. And this has to deal with the size of the atom. We know as we go down the periodic table, the atoms are getting bigger, right? Because we go from n equals 2 to n equals 3, 4, 5, and 6. So the layers of our onion, right, of our atom are getting bigger and bigger and bigger. And when they do that, that means that the outside, the valence shell electrons are getting further and further away from the center, right? If here's the center of our atom where all our protons are, if we have 4 or 5 layers, the electrons are way out here. So the pull between the protons in the center and the electrons way out here is way weaker than the pull of the protons here and the electrons that are right here. So electronegativity increases when we have a smaller atomic radius than when we have a bigger atomic radius. And that's because the pull for those electrons, it's closer to the protons because it's smaller. The bigger it gets away, those electrons are more weakly associated with the protons in the center. We have been talking about covalent bonds, and we've been saying how they're shared. And up until now, you may have been like, okay, cool. These electrons are shared. They must be shared equally, just like we learned in kindergarten, right? We share our toys. Unfortunately, just like everything else in the world, covalent bonds aren't so clear-cut. Sometimes the electrons shared in the covalent bond are equally shared. This often happens when we have two atoms that are the same. If we have two atoms that are the same, and I mean identical, hydrogen and hydrogen, chlorine and chlorine, carbon and carbon, they're going to have equal electronegativities, right? It's the same type of atom, so it's going to have that same, an equal amount of pull on the electrons. Or if they're similar in their electronegativity, they would have an equal pull on the electrons. So they share the electrons equally. If we have a covalent bond, the electrons live pretty much in the center of the bond. Sometimes, however, that sharing of the electrons is not so equal. And this happens when we have a pretty large differential in the electronegativities of the two atoms that are doing the sharing. For example, if we have a hydrogen and a chlorine, hydrogen has a very low electronegativity. Chlorine is fairly high. Well, that means that when they're sharing those electrons, the electrons are going to hang out closer to the chlorine than they are to the hydrogen. They're still being shared, but they're not being shared equally. It'd be like playing tug of war between a kindergartner and a football linebacker. It's just, they're not going to be shared equally. And when this happens, the electrons inevitably end up living at one end of the bond more than they do at the other. And when this happens, we end up with a slightly positive, slightly negative kind of pull on the bond. Now, please, there's very, very important that we see this Greek symbol here. Basically, it's telling us slightly positive, slightly negative. This is still a covalent bond. It's not ionic. I repeat, this is very, very important. This is not an ionic bond. Write this all over this page. This is not an ionic bond. Slightly positive, slightly negative. No one gave up an electron, no one took an electron. They're just being shared unequally. The reason this is slightly positive and the reason this is slightly negative, if the electrons are living closer on this end, that means there's more electronic density down at this end of the bond. Electrons are negative, so there's going to be a slightly negative kind of vibe to this end of the bond. Because all the electrons are down hanging by the chlorine, that means there's kind of a deficiency of electrons on the hydrogen side of things, which would make this slightly positive. But again, in no way are these ions. No one gave up an electron, no one took an electron. They are sharing them still. They're just sharing them unequally. Electronegativity is kind of a spectrum when it comes to the bond, and polarity of a bond is kind of a spectrum. We can have something that is completely nonpolar. We can have something where there might be a slight difference in their electronegativities, but it's not enough for it to really pull the electron. And so this would be a nonpolar covalent bond or a polar covalent bond. And a polar covalent bond is where we're going to start seeing that slightly positive, slightly negative thing. And then the extreme of that, right, would be an ionic bond, where instead of being slightly positive, slightly negative, where they're sharing them and the electrons just kind of live on one end, someone gave up electrons, someone took on the electrons. So this is kind of a nice chart to look at when we're thinking about things. Couple things to think about logically. It doesn't matter how electronegative an atom is, like chlorine, very electronegative, right? But if it's bound to another chlorine, it's still going to be nonpolar, that bond, because of the fact that it's being equally pulled. This would be like two linebackers, right? Two kindergartners, two linebackers. Another rule of thumb, CH bonds, carbon-hydrogen bonds, those will always be nonpolar. Just rule of thumb, write it down now. Carbon-hydrogen bonds will always be nonpolar. Hydrogens mixed with halogens will pretty much always be polar. And then remember, when we have a metal and a nonmetal, that would be ionic. Okay. Again, I would encourage you to maybe stop here, kind of grab your head around your notes, maybe do some reading in the textbook, go try some of the homework problems, give yourself kind of a mental break before moving on to the next and last section in here. One of the last topics that we're going to talk about in this section, or in this chapter, is called VSEPR theory. VSEPR theory stands for valence shell electron pair repulsion theory, and that's got a lot of words in it, but we can break it down and it makes a lot of sense. Valence shell. Okay, we know what the valence shell is. Valence shell is the outermost shell of the atom. Valence shell electrons. Okay, valence shell electrons are the electrons that live in the outermost shell of the atom. Valence shell electron pair. Oh, okay. Well, I know that, valence shell electrons kind of pair off, right? And that when we have valence shells of one atom intermingling with valence shells of another atom, that we can get a covalent bond. So maybe we're talking about those pairs. And then repulsion theory. Well, repulsion, we know that repulsion means that they push away from each other. So electrons that are two negative forces coming too close to each other might push away from each other. So that's pretty much what's going on here, is we're talking about in the valence shell of an atom, we have electrons. And all those electrons are tethered, right, to that atom, but they're all negative charges. Negative charges don't want to hang out next to other negative charges. Think about when you were a kid and you played with magnets. If you put two similarly charged magnets next to each other, right, they would want to push away from each other. They would repel each other. Same thing is happening with our electrons. The electrons that are around a central atom are going to try and arrange themselves in a way that will put them as far away from each other as possible, while they're still being tethered to that atom. Now, it's also important to remember that an atom is 3D space, so we're going to be talking about this in 3D space. There are some resources available to you through our Canvas page and the resources page that are good for those of you who struggle with kind of visualizing 3D space. So you can go check those out. Another really good thing, if you have access to it for cheap, are modeling kits, chemistry modeling kits. If you don't feel like dropping 50 bucks, go buy a bag of gumdrops and some spaghetti from the grocery store, and that will do pretty much the same thing that the $50 modeling kit will do. So we'll talk about that a little more. So when VSEPR theory helps us kind of figure out the shape of molecules, molecules arrange themselves in very specific, repeatable ways. And it's kind of crazy to think about, right? If I throw a carbon atom and 4 hydrogens together, they're always going to arrange themselves and bond in a very specific shape. And this theory helps explain why that shape happens and how we can predict that shape. And this is important because this will help us figure out if the overall molecule is polar. Up to this point, we've talked about a bond being polar, but then when we start getting bigger, more and more atoms bound together, we have a molecule, and then we can start talking about whether that molecule is polar. So it has a couple steps to it. The first would obviously be to write the electron dot formula for the molecule, not the molecule. Sorry for that. Lovely little typo there. Kind of cute though. Then we're going to arrange the groups in a way that we can kind of minimize those repulsions. How are we going to arrange those groups around our central atom in a way where they get to be as far away from each other as possible while still being attached to the molecule? And then lastly, we can use those different bonded atoms and their arrangement to figure out a shape. So in your resources slide, I have a whole extra kind of more in-depth, a lot more example VSEPR theory kind of like mini lecture that you can look at as well. But we're going to go through the basics here. So when we have 2 electronic groups, so we're talking about a central atom. We can only do 1 atom at a time when we're talking about the shape around the atom. So in this case, we're talking about the central atom, beryllium. Remember that beryllium can be an exception to the octet rule. And because of that, it's okay with just having 4 valence shell electrons, but coming from two chlorines. And this would be considered an electronic group. This chlorine is one electronic group. This chlorine is a separate electronic group because it's branching out this way and this way. If we have 2 groups, the best way we could arrange it where those 2 groups get to be as far away from each other in 3D space as possible would be to put them 180 degrees away from each other. And just like you would think if you had, balls and sticks, so your gumdrops and 2 pieces of spaghetti, just like that, this would form a linear compound. Now what's going to be tricky here is that for VSEPR theory, when we're talking about an electronic group, we are talking about actual groupings, not number of bonds. So in this case, even though there are double bonds here, this still counts as 1 electronic group, this counts as a 2nd electronic group. So that can be a little tricky for students. We can also have 3 electronic groups around a central atom. In the example of boron. Again, boron is another one of those kinds of wacky elements that is capable of breaking the octet rule. And what we can have happen here is when we have 3 electronic groups, around the central atom, they're going to separate themselves 120 degrees away from each other. We call this shape trigonal planar. It's planar because it's flat. It's flat like a plate. So again, if you took your gumdrops, you'd put one in the center and then 120 degrees flat out from each other. The other way we can have 3 electronic groups is by having 2 atoms and possibly a lone pair. A good example of this is SO2. In this case, when we draw out the Lewis dot structure for SO2, we have an oxygen where we have a double bound oxygen on one side, a single bound oxygen on the other side, and then a lone pair sits on the sulfur. This would be considered 3 electronic groups. We have 1 electronic group here, 1 electronic group here, and a 3rd electronic group here. So again, we can kind of see how this is a trigonal planar shape, right? There's 3 120 degrees away from each other, approximately. We actually, because this lone pair is kind of big and self-important, it is actually going to repulse more than a bound electronic group, and so it actually kind of pinches these in. So this is actually a little less than 120, and this one is actually a little more than 120. But we call this molecule bent. Electronically, it's still trigonal planar, but if we were to look at the actual shape of the molecule, right, we can't see the electrons. We can't see this when we look at the molecule. We just can see the bound atoms. So we call this shape bent. Next would be 4 electronic groups. In a molecule with 4 electronic groups, the really good example that we always go to is methane, CH4. And this group, right, if this is our electronic dot formula of it, it's drawn in a tetrahedral arrangement, we call it. And this is kind of hard to visualize. The best way I could tell you to do it is if you pretend that your belly, like if you stand up right now, pretend that your belly button is the carbon. Put your arms up in the air, and that will represent these 2 hydrogens. Put your arms up in the air to the side, to the left and right of yourself, up above your head. And then if you put your feet going the opposite way, right? If these are your 2 feet, right? Here's your head, the top of your head. Your belly button's right in the center, right? If you look straight down, your arms are up and your feet are out, like this. That would be tetrahedral in shape. That is one of the best ways to describe it in a stationary document like this. I have posted a lot of resource videos to help with visualizing tetrahedral shape. The other way we can look at tetrahedral would be to say, okay, I have 4 atoms bound, or I could have 3 atoms bound and 1 lone pair, or I could have 2 atoms bound and 2 lone pairs. So those will give us different shapes, just like the lone pair gave us a different shape for the molecule in SO2. When we have 3 atoms, or 3 bound portions and 1 lone pair, this will be tetrahedral in its electronic arrangement, but we would call this trigonal pyramidal in its shape, right? Because that lone pair sits up here and we really can't see that. So we're left with this kind of pyramid triangle structure. The great example we always use, again, as always, water, when we have something that is electronically tetrahedral, right? 4 groups, 1, 2, 3, 4 groups, but molecularly we can't see those lone pairs, so we end up again with a bent shape. So this table is kind of a nice resource. Again, I would encourage you maybe to print this out or redraw it in your notes. It kind of helps you go through and identify the different shapes. So we have electronic arrangements, and then we have molecular arrangements. Being able to know a shape is really important when we start looking at the molecule as a whole and trying to figure out whether it's polar or not. Sometimes we will have molecules where it has polar bonds, but overall those polar bonds are arranged in such a way that they cancel each other out, making the overall molecule not polar. And that will be really, really important when we start getting into Unit 2 and start talking about reactions that can occur. So, nonpolar molecules. If a molecule does not contain a polar bond, it cannot be polar. That should be pretty obvious. No polar bonds, no polar molecule. However, we could have a molecule where it does contain polar bonds, but those polar bonds are symmetric. So for example, in CO2, this is a linear molecule. CO is a polar bond, and this CO is a polar bond. But I can draw a line, I could cut a knife right down the center. It's symmetric, so this is pulling equally to this pulling. And because of that, overall, there is no polarity to the molecule as a whole. The same thing would happen with CCl4. Each of these carbon-chlorine bonds is polar, but because it's in a tetrahedral arrangement, which is symmetric, overall there's no polarity to the overall molecule. Now, when we see these arrows, your textbook explains these are what we would call like a polarity arrow, and it's just a visual way to represent that polarity in the bond. The head of the arrow will always go towards the negative side. The tail of the arrow kind of has a little plus charge built into it, as you can see here. So the tail will always point towards the positive end of the bond, the slightly positive end of the bond, and the head will always point towards the slightly negative side of the bond. So, a good example to try and practice this with is to determine the polarity of the H2O molecule if we're looking at water. So the first thing we can do is we first have to draw water. So we know that we're going to have water as H2O. That oxygen needs 2 more valence shell electrons and each hydrogen needs 1. So they're going to have each hydrogen share and make a covalent bond with the individual unpaired electrons of the oxygen. So we have something that looks like this. Then we're going to identify that there are 4 electronic groups around that central oxygen. 1 here, 1 here, 1 here, and 1 here. 2 of these electronic groups are lone pairs. 2 of these electronic groups are bound atoms. When we look at the polarity of each bond, we know that the HO bond is polar, that the slightly positive side of the bond is going to be at the hydrogen end of things, and the slightly negative side of the bond is going to be at the oxygen. In addition, this oxygen has lone pairs on it too, so it's even more slightly negative. Now, remember those lone pairs are going to be pushing down on these hydrogens and pinching them closer together. And because of that, when we look at the polarity, this isn't linear like CO2. It's bent. So there is no symmetry here. I could cut right along the bottom of these bonds right here and cut this, and I would have a portion of it that would be slightly positive and a portion of it that would be slightly negative. And because of that, this molecule is polar. This becomes very, very important, being able to determine whether a molecule is polar or nonpolar when we start having molecules interact with other molecules, right? So at this point we've gone from atoms, or smaller than the atom, right? The proton, the neutron, and the electron, to building a whole atom, and then that atom interacting with other atoms to form a molecule. And now we're going to talk about how molecules can interact with other molecules. These are called intermolecular forces. We can have intermolecular forces and we can have intramolecular forces. When we're talking about the interactions that occur within a molecule, like a covalent bond or an ionic bond, those would be intramolecular forces. Similar to how we have intramural sports, Those are sports that happen just at one campus. Inter-ER molecular forces are the forces that occur between different molecules. Just like international is, the interactions that occur between different countries, inter-ER molecular forces, also written as IMF, standing for intermolecular forces, describe kind of the interactions that are possible and can occur between different molecules. So whenever we're talking about inter-ER molecular forces, we have to have more than one molecule present. The first type of molecule, intermolecular force that we're going to talk about are dispersion forces. These will be the weakest of all the attractive forces between molecules. And in fact, pretty much everything has this. These are also called temporary dipole, London dispersion forces, let's see, what else are they called? Intermittent forces. Again, depending on the resource you use, sometimes they are called different things. But this is caused by a temporary dipole that develops when the electrons are not distributed evenly. So this can happen even when we have a nonpolar covalent bond. So in a nonpolar covalent bond, we know that electrons, even though they're hanging out in this bond and they're probably pretty equally shared, electrons are always constantly moving, right? And is it possible for just an instantaneous moment of a second that both electrons hang out on this end of the bond, right? Just for a moment, and then the next instant they're somewhere else, because they're always moving. If they do that for just that brief instantaneous moment, this would be slightly negative, and this would be slightly positive. And that's exactly what happens. This is constantly moving, and this is why it's the weakest of all the forces, is because they're very temporary. They're very instantaneous. They come and they go. And it's this kind of temporary polarity that occurs. The next type of inter-ER molecular force that we can experience is a dipole-dipole interaction. And this is where we actually have a real polar bond, not an intermittent one, not an instantaneous one where we actually have a slightly positive side of the bond and a slightly negative side of the bond, an unequal sharing of the electrons. In that case, the same attraction that we saw instantaneous and temporarily happening in the dispersion forces is happening constantly in a dipole-dipole interaction. And that's the slightly positive side of one molecule being attracted to the slightly negative side of another molecule. Now, we use this dotted line to represent attraction. They're not bound. This fluorine is not sharing electrons with this hydrogen. This fluorine is married to this one. This hydrogen is married to this one. They're just kind of, checking each other out. In terms of our strength, we have one more force that we'll talk about in a little more detail, and that would be hydrogen bonding. Hydrogen bonding is a special kind of dipole-dipole interaction. It's when we have an extreme dipole. An extreme dipole is going to be a hydrogen bound to either a fluorine, an oxygen, or a nitrogen. When this happens, we're going to have an extreme dipole moment. The hydrogen's so small, it's such a slightly positive, and the fluorine, oxygen, or nitrogen is so a negative and so large that we're going to have a really strong slightly positive and a really strong slightly negative. So the attraction here is going to be greater than for, say, just a plain dipole-dipole, where we have slightly positive, slightly negative, and then slightly negative one molecule being attracted to slightly positive of a different molecule. So when we kind of look at the spectrum of these inter-ER molecular bonds, forces, they're not bonds, I'm terribly sorry, intermolecular forces, they're not bonds. Dotted lines are forces, attractions, not actual bonds occurring. Dispersion forces, London dispersion forces, instantaneous dipole, whatever resource you're looking at that calls it, this is the weakest of all the interactions. All molecules, polar, nonpolar, whatever, they all experience dispersion forces. Next are dipole-dipole interactions. These are slightly stronger. They occur between polar molecules. A special kind of dipole-dipole interaction is a polar molecule where it's a hydrogen bound to either an F, an O, or an N. And we call this hydrogen bonding. I did not come up with this name. It is a terrible name for a force, but that is what it is, and that's what we have to deal with. And then obviously the strongest type of intermolecular force would be an ionic bond. But when we're talking about covalent bonding, we're talking about these three right here. Okay, that was the whirlwind of Chapter 4. It's very, very important that you utilize the extra time that we have during lecture and up and through till next Tuesday to do your reading and work on the homework. This will be great practice and will really help ensure that you solidify these concepts. I'm sorry that we had to do a pre-recorded lecture today, but I am available via email for you to reach out with questions. I'm sure there will be plenty when we meet on Tuesday. We'll have to deal with our quiz and then we'll get into questions. So good luck, do your reading. Please reach out to me via email with questions and I'll be able to start answering them for you. The resources posted in this week's module will also be very, very helpful. Let me know if you have any questions. Thanks for listening.